In today's video, we are going to work on transforming functions just in general. So to get you going on that, I'm going to have you do the following two warm-ups. So pause the video, please, and I want you to graph that cubic without making a table, just using transformations based on what you did the last 2 days. And then lastly, I want you to write an equation for a square root function with that starting point and that contains another point. So pause it for a minute and go ahead and do these. Okay, so we're going to start with our writing and then we'll go back to graphing. So when we are writing an equation for a square root function, I know we have our parent function y equals the square root of x. In the transformation form, y equals a square root x minus h plus k. So now what I have to plug in there is my locator point and then figure out what my a value is based on my random point that it contains. So h and k is the locator point for all square root functions, and that's that starting point. So the locator point for all square root functions is your starting point, because the square root function starts and goes like this, or goes this direction, or reflected. So those are kind of the 4 different options for a square root. So I put my h and k in. So y equals a square root x minus 1, and then plus k, so minus 3. And then the last thing I have to do is substitute in my coordinate point. Just like always, when I have one parameter left to solve for, I plug in my point and I solve for a. So 5 equals a times the square root of 5 minus 1 minus 3. So simplifying that, make sure you do order of operations. 5 equals a square root of 4 is 2 minus 3. I cannot combine these together because of multiplication. Add the 3 over, 8 equals 2a. A therefore is 4. So we have our equation, y equals 4 square root x minus 1 minus 3. So this is a square root function with a starting point at positive 1, negative 3 with a stretch factor of 4. So that's how we can use it. Okay, the other one is going vice versa. Here's an equation, graph it. From this one, it was here's information that we could pull from a graph, write the equation, and whereas this one is just here's my equation and graph it. So I have a cubic function. So you need to understand what the shape of the parent function for the cubic is. So when you made your parent function and transformation packets, so you did all of the 5 different functions, you have to look inside this table here and think of all the possible values. I can put 0 in, I can put 1 in, 1 cubed is 1, I can put 2 in, 2 cubed is 8, I could put 3 in, but that's getting really big. Going negative, negative 1 cubed is negative 1, negative 2 cubed is negative 8. So that's that parent function that you're going to do with cubes. We did the same thing with squares. You're going to do that always. You're going to think of what that parent function is, because from this parent function, we're now going to do our transformations. So from the parent function, I have a locator point of 0, 0. Every cubic looks like this. And there's that turning point in there. It looks like it's a half of a parabola and then also a rotated half parabola. So based off of that, that is my 0, 0 point. So that point is now, so my locator point is positive 1, negative 3. So on my graph, I go 1 over, 3 down. So there's my locator point. That's my 0, 0. Now I have this stretch factor of 2. So if my stretch factor was just 1, if my a value was 1, from here I go 1 over and 1 up, 2 over and 8 up. 1 to the left, 1 down, 2 to the left, 8 down. So I could just do that from this graph. But I'm vertically stretching it by a factor of 2. Therefore, from my locator point, instead of going 1 over and 1 up, I'm going to go 1 over and 2 up. And on the other side, 1 over and 2 down. Now it looks like a line, but it's not. That's where that 5th point comes in. That's why a lot of times we graph 5 points. Not always, but a lot of times. And then from my locator point, it goes 2 over and 8 up. But this time it's going to go 2 over and 16 up. Downfall, that's going to be off my graph somewhere. And then it'll be 2 over and 16 down. Again, way off my graph down here. So we're just going to try to vertically stretch this. Again, I apologize for my not so good curve. I always start from the locator point and then go through them and then go up or down. And there is my stretched cubic. And I can always check with some other values, but we don't want you to have to make a table for it. But at least from this way, you can find that locator point and then do your stretch factor. Okay, so we're going to formalize all of the different transformations that you worked on the last 2 days. So in geometry, you transform figures just like you transformed your parent graphs. So today you're going to look at more of the geometric transformations. That happens when you take the opposite of x before applying the operation. So we're going to investigate f of negative x. But before we do that, we're going to look at some of those basic transformations that you did. So take a moment, go through these before I start telling you what to do. Go through these and see what kind of transformations do you think they are. Are they vertical? Are they horizontal? And then what do they do vertically? What do they do horizontally? So go ahead and pause. Okay, so what kind of transformation if you took your y value and replaced it with y plus k? So that y value, that's vertical. So this is a vertical, and then it just adds k, so it moves it up. So that's a translation. What kind of geometric transformations occurs when you replace f of x with the opposite of f of x? So again, f of x is like your y values. So what happens when I multiply my y values by a -1? Well, that's going to be a reflection. Now, which axis is it? So if I'm changing the negativity of y, so like here's my graph. So I have a point here at say 1, 2. If I multiply my y value by -1, now instead it's 1, -2. Which axis did we reflect it over? The x-axis. Okay, now we have the x inside. This is f of x minus h. So now the transformation that's happening is it's affecting your x value. And since it's adding, that's going to be a translation as well, and it is a horizontal translation. This one is a, and it's times f of x. So I'm multiplying my y values. So that's going to be a vertical. And then what do you call it when we stretch or compress it? Do you remember? Dilation. And again, that's just the stretch or compression. And then f of negative x, or f of the opposite of x. So again, I take those x values and I change the negativity of x. That is affecting your x, but it's a multiplier of a negative, so that is a reflection. And this is going to be a reflection over, so if I'm changing the negativity of x, so this point here can be like 4, 1. So I'm changing my x value, so now it's -4, 1. That's reflecting over the y-axis. So when I change the negativity of x, it reflects over y. When I change the negativity of y, it reflects over x. So before we get on to the next part where we're substituting in the opposite of x, would you please take a moment and go ahead and graph these 5 functions. These are the parent functions. We're leaving out exponential functions at this point. We're just going to focus on these 5. So I want you to graph the parent function for them with no calculator and make the most basic table you can. Just like for our warm-up, when I made my table for y equals x cubed. So this is exactly the table that I'd be making for my cubic function. So I want you to graph all 5 of these, again, making that table piece. Okay, so a square root function, I can't put negatives in, so I started at 0. Absolute value, I can do negatives and positives, so I get that set of a composite of 2 linear functions with restricted domains. Cubic, we did that one already. Quadratic, we've done a lot of those. And then the reciprocal function. So keeping in mind the reciprocal function always has asymptotes. So remember that I can't divide by 0, so there's a vertical asymptote at x equals 0. And then you found when you graphed this, there ends up being also a horizontal asymptote at 0. Those asymptotes will shift around depending on whatever your shifts are. Realistically, when you graph this, I just usually graph a couple points and then I follow my asymptote behavior. So super quick, just have your asymptotes wherever they belong, and then at least a point on each side, left and right of the vertical asymptote, and then you get your follow your asymptote behavior. Okay, so the next part, we want to substitute x in, the opposite of x in for x into each of the parent functions and then graph it. So here's what that means. So you're substituting the opposite of x in for x, and then we're graphing the new function. So in the blue here, So in this square root function, this is my original function. If I typed in my calculator y equals square root opposite x or negative x, it gives me the red. So remember what we talked about earlier on the very first page of our notes. If I change the negativity of my input, it reflects over the y-axis. So that's what we have here. The blue is the original graph, and the red is the opposite of x. So what do you notice happens with this one here and this one here? The same, right? Whether I graphed f of x or f of negative x, they are the same. However, for these cases here, that is not the case. But what you will notice is, see this function here, this blue? Think about it as rotating it. If you rotate it around, it rotates onto itself. So this here rotates onto itself down here, which ends up being that this here rotates around here. And the same thing goes here. So this one rotates about the origin onto itself here. And that, when I reflected that over, those rotate around as well. This does not rotate onto itself, the original function, that is. The original function does not rotate onto itself. The original function, how does it go onto itself? It reflects. This reflects onto itself. So the original function is a parabola. This reflects over the y-axis on itself. This one here, I know it's getting kind of messy. My original function does not rotate onto itself. Sorry, I said rotate. It does rotate onto itself. It doesn't reflect onto itself, whereas this one here and this one here reflect onto itself. So these two here rotate onto themselves, and this one does nothing. So there's some commonalities because of that feature. And I can do it algebraically as well. So I'm going to look at the two that reflect onto itself. So this one here and this one here reflect onto itself. So if I algebraically substitute negative x in, so I put negative x in, well, what's the absolute value of negative x? That's still just x. So therefore, if I plug in a negative x, it doesn't matter. I get the same output. Same thing here. If I substitute a negative x in, so if I substitute that negative x in, what's a negative x times a negative x? Positive x squared. So whether I put in a positive x or a negative x, I get the same output out. So we say that f of x is the same thing as f of negative x. Now for the other two cases, those rotated onto themselves, so that's these two cases here. If I substitute in a negative x, and so I take negative x to the third power, a negative x times a negative x times a negative x, odd number negative, so that's negative, but it's still x cubed. This is different. This means I'm going to take negative x times itself 3 times. This one means I'm going to take x times itself 3 times and attach a negative. So this is f of negative x. Well, this here is exactly the same thing as this, but the opposite. So therefore, if I put in f of negative x, it's the same thing as the opposite of if I put in f of x. So if I change the negativity on x, I change the negativity on y. That's my output. If I change the negativity on my input, I also then will change the negativity on my output. That is also the case down here. So if I put in a negative x here, it's the same thing as 1 over the opposite of x, which is the same thing as the opposite of 1 over x. So when I change the negativity of my input, it changed the negativity of my output. So f of negative x is the same thing as the opposite of f of x. And then this one, I saved this one for the end because it's just odd. I shouldn't use the word odd, it's different. So if I put the opposite of x in here, all this does is changes what my input values can be. So instead of being able to put positive numbers in for x, I have to put negative numbers in for x. But I don't get anything else out in terms of the different types of numbers. So this is just its own case. Now the reason we went through all 5 of these is because based on this, I have these graphs. So again, I'm looking at these two are the same, just like those two are the same. The cubic and the reciprocal are very similar in stature to that one because we have what are called even, odd, and neither functions. So if, make this smaller, if when I substitute opposite of x in, so if I change the negativity of my input and my output is still the same, that is an even function. So list which ones are even. If I change the negativity of x and it changes the negativity on y, we call that an odd function. And then we have a lot of functions that are neither. So take a moment, fill this out. So even would be x squared, an absolute value of x. Odd would be the reciprocal and the cubic. And neither would be the square root of x. Additionally, another neither one would be the exponential function. Okay, there's a lot that are neither. There are very few that are even or odd, but when they are, they have those great characteristics that the original function, when it's even, reflects onto itself. When it's odd, the original function rotates onto itself. So feel free to put a little note there, but you can also see it algebraically. This concept's a little different. We will definitely talk about it tomorrow.